This video is about the OSI reference model, which has been provided by ITU in 1983 and ISO in 1984. The abbreviation OSI stands for Open Systems Interconnection. Open in this context means that the specification is available to anybody and is not proprietary. In the 1970s, the situation has been that computer vendors delivered hardware and in addition networking software. However, the software only allowed for communication with other computers from the same vendor. Therefore, the aim in 1977 was to develop a networking architecture which is vendor independent. The main idea is to use a layered model where lower layers implement a basic functionality which can be used by higher layers. The OSI model is a logical model which provides a general structure for a communication system. However, it is not well suited to be directly implemented in software. Such an implementation would be quite inefficient due to the clear separation between the layers. As a result, many unnecessary copy operations in computer memory would be necessary. This slide gives an overview of the model. It consists of 7 layers which are implemented by end systems. Transit systems, which are also called intermediate systems, only implement a subset of the layers. Here we have an example of a router which implements the lowest 3 layers. On each layer we find entities which implement the functionality of the layer. Protocols are used for communication between entities on the same layer in different systems. Now we start to take a look at the details of each layer. There is a general distinction between the 4 lower layers, which are called the transport-oriented layers, and the 3 upper layers. The 4 lower layers provide an end-to-end transmission of data between applications. From their perspective, it is unknown and makes no difference what the data semantics is. The layers provide a general data transport mechanism where the way how to realize the data exchange to be able to provide network applications is the main concern. The lowest layer is the physical layer. Here the question is how it is possible to transmit bits over a given medium. Examples of media are copper cables, fiber, or the air. For some media it is possible to specify their features. For copper cables it is possible to define the way how they have to be manufactured so that, for example, certain attenuation conditions are fulfilled. In addition, plug specifications can be made. Furthermore, the use of line codes is a task of this layer. This means to define how zeros and ones are represented on the medium. The way to transfer bits on the physical layer is specified in a way so that it works quite well on average. However, if there are errors in bit transmission, then the physical layer does not take care of it. It has no mechanism to detect or correct bit errors. This deficit of layer 1 makes us move on to the data link layer, which takes care of the data transmission between devices which are directly connected. The transmission is improved by protocol mechanisms so that it seems that there is a perfect medium without any errors. However, the errors are detected and corrected by the protocol, in particular by resending lost data. For doing so, it is necessary to regard the bits no longer as an unstructured bit stream, but to define data units with a clear structure. Such a data unit is called a frame. Buffers are introduced in this layer both for the sender and the receiver side. The buffer on the sender side is needed to store data units which have been sent but are not yet confirmed. The sender is then able to resend them if needed. The buffer on the receiver side is to store data which has been received but waits for its internal processing in the system. This buffer is important for flow control. The scenario of flow control is a sender that is able to send data quickly, but the receiver is slower and cannot process the data as fast as needed. Flow control is therefore a kind of feedback mechanism to tell the sender to send less data. Another major task of the data link layer is called medium access control. If there is a shared medium for example in a bus topology, then it is necessary to control the access to it. Otherwise, if all systems send at arbitrary times, then there would be a lot of collisions. In addition, there are addresses which are used in this layer. In reality, these addresses are the MAC addresses, which are named according to the medium access control. The communication on layer 2 is only suitable for devices that can directly communicate with each other. To allow for end-to-end communication, which may require several forwards by intermediate systems, pathfinding mechanisms are needed, which we find on OSI layer 3. This layer, which is called the network layer, requires another way of addressing where addresses are hierarchically organized. Otherwise, there would be scalability issues in worldwide communication. In reality, these addresses are the IP addresses which belong to the Internet Protocol. Layer 3 may use individual layer 2 links to realize parallel communication. On this layer, the error detection is rather simple, so that bit errors are just detected and data units can be dropped, but there are error messages only in severe error situations. As a consequence, data can get lost in end-to-end communication, but the network layer protocols do not take care of the situation. The transport layer is the fourth layer in the model. It extends the end-to-end communication between devices to an end-to-end communication between applications on the devices. Assume that on your computer you are currently browsing in the World Wide Web, but in parallel your mail client is active. It has to be distinguished whether a data unit which is sent to your computer is part of an email or belongs to a web page that you currently retrieve. For doing so, another way of addressing is needed to select between different applications. In reality, this kind of addressing is called port numbers. On this layer, we find sophisticated error detection and error correction mechanisms to make sure that nothing is lost in the end-to-end communication. In addition, there is flow control and congestion control. Flow control is available on layer 2 as well, but this time it is an end-to-end flow control. This means that the data source located somewhere in the network does not overload the receiver that may be located in a completely different part of the network. Congestion control means not to overload the network itself. That is, it takes care that senders reduce their data rates if intermediate systems inside the network receive too much data, which they cannot forward as quickly as needed. On this layer, there is again a multiplexing, this time of the end-to-end path. The layers 5, 6 and 7 are called the application-oriented layers. Their idea is to separate several tasks for implementing an application. However, it has turned out that this concept has not been adopted in reality as foreseen. Nevertheless, the tasks of these layers are still relevant. For applications, the semantics of the communication is important, and it is also important to consider the roles of different users. Layer 5 is called the session layer. A session is a communication where it is relevant for the current communication what has happened before. Let us assume you want to access a web page which is password protected. Then it makes a difference whether you have already logged in using your password or not. In addition, the session layer takes care that there are no inconsistencies if communication is interrupted, so transactions may have to be rolled back if they were only partially executed. The main idea of the presentation layer is to abstract from heterogeneous devices. This means a programmer can write code for the application in a device-independent manner, and it is then automatically adapted to given devices. This is, for instance, relevant for variable type representations or may also be interesting for different screen resolutions. Data compression and encryption-decryption is also part of this layer. Finally, there is the application layer. On this layer, data communication based on application needs happens. Since this exchange is strongly application-dependent, it cannot be specified any further in this general view. Examples of applications include email, file transfer, and the World Wide Web.